All right, welcome everybody to Data Science Office Hours. We're very excited this week to be with you, and we're discussing a great topic. We're missing our European contingent. Andreas is feeling under the weather, and Terry's on a world tour right now. Be sure to keep up with his posts. Right now, be sure to. We're talking about an incredibly important topic in data science, something that that you'll encounter almost in every project where you're going through the data science pipeline. And it's our goal with the data science office hours right now is to take you through the data science pipeline, where we start at the beginning of defining a data science question. And today we're talking about feature selection and feature engineering. And these are two very important topics that are often related, but they're somewhat distinct. And the approaches that you take and the considerations that go into feature engineering and feature selection often depend on the industry that you're in, or the type of question that you're answering, and even the algorithm that you choose. And part of what makes data science so complex is there's not a one-size-fit-all solution. And we've talked about this a lot in data science office hours, that there's so many considerations based on what your outcome is who you're presenting your data to, or how your model will be used in production. That part of being a good data scientist is knowing what the trade-offs are and knowing how to navigate that space. And so that's something that's definitely true about feature engineering and feature selection. And I think maybe to start off, we could start off with some definitions of what do we mean by feature selection and feature engineering. And I'll kind of start off with kind of how I understand it, and then I'll let some of the others chime in as well. But so feature selection, the idea behind that is that sometimes you're faced with a situation where you have so many variables that you need to reduce the dimensionality of your data set, where you need to focus on a subset of variables and include those in your model. And if you choose the right variables, it makes the process of training a model go a lot quicker, because you're not trying to use variables that are going to be less predictive. There's this thing also in computing called the recursive dimensionality, where the more dimensions or features or variables that you add to a problem, the more complex that it becomes. In the past, this was a massive problem in terms of computational speed, but with the increases in computational power, this is not as big of a concern as it was. But still, if you have like a medical data set where you can have up to millions of variables per patient, this can be a huge concern. And so you often need to pare that down and discard the features that are not going to give you good predictive value. So that's at least one definition of feature selection. And I don't know if anyone else has anything to add to that.
I'll jump in. So something that I want to say before we talk about feature selection and feature engineering is like even defining what a feature is. So like if you ask somebody 10 years ago about a feature, like what it would mean to have features from an image, like it wouldn't make sense, right? Like they would say like, well, what does that even mean? What do you measure about an image that you can turn into features? So I think over time that's going to matter a lot, because the way that we think about features, at least when you first learn about them, is like they're numerical. And people tend to just think, oh, I just need numbers to be able to predict things. But I think as we start getting, particularly with things like deep learning, particularly as these fields advance really quickly, what becomes a feature and what we can hope to measure also changes a lot. So I don't, and the reason that was partially me saying that because I wanted to share that, partially because Bo took all of the good things that I wanted to say. So he's already way ahead. So I'm going to pause there and let Fabio or Sarah jump in.
Hey, So I think those were really two good points. And I agree with you, Eric, because this area is really changing really fast. So the idea that we have of what's a feature and how to extract a feature from something has changed. Even I think the last 5 years has been really like dramatic change in what we can do with different kind of data. And so I think one of the other important steps in feature selection is need to understand what's going on with the problem, because it's okay to use algorithms, and we may talk about that later in this office hours about like the frameworks that you use or tools. But you need to have an intuition of what may be important at first. And the thing here is that you have to challenge yourself, because sometimes you may think, okay, so I think for this problem, this will be the most important variables, and in the end, they're not at all. So that intuition that you have in the beginning is not the same as the one you create when you're performing data science over and over and over again. And when you go through the process of a pipeline of transforming variables and creating new variables, and also selecting those variables to I don't know, to feed an algorithm, I think you start getting an idea of the different kind of problems you can solve, and how different a data set can be explained. Because sometimes you may see some variables in a data set, and you say, hey, I have nothing here. And then after you're doing this feature engineering and transforming and also selecting those important variables, I think you can have a very idea of what you're having right now. I think the feature selection part is not as easy when you have a lot of features. I don't know if we can. I think someone asked me yesterday. It's like, hey, I mean, I know you're going to talk about features engineering and selection, and what about when you have I don't know, thousands of features or thousands of different variables that can explain a problem? How I mean, what are the I mean, I have these frameworks and tools, but how would you guys tackle that problem of having a lot of different variables and selecting those 10 or 15 or 20 important variables?
Yeah, great stuff. I echo everything that you guys said. And something that I'd like to add on this is that the way I think about feature selection and feature engineering is it's more like an art than a science. And what you'll tend to notice is when you go into like a new field, so let's say these are things that you expect as the biggest challenges, is that those who have been in that space the longest, who have the most domain knowledge, are probably going to know more about what features are most important. And so that's kind of where us as data scientists who are going into these fields kind of have to engulf ourselves into the industry that we're trying to tackle and try and understand what KPIs are important and what we're trying to predict and how those KPIs and all the features that we have in our data set are related. So yeah.
All right, thank you, Sarah, Fabio, and Eric. A couple comments. So, I've spent at least the past year, more time than that, in life sciences, and this is an area where there typically are lots of features, especially if you're measuring genomic or proteomic data, proteins, lipids, or other characteristics of the body. You can generate a lot of data points about one individual, and obviously, if you think about everything you can measure about a person's health, it would be absurd to think that every single variable that you could measure relates directly to some condition that that person has. There's going to be some proteins or some processes, other things that you measure that correlate or cause a disease, and there's going to be other things that are just completely irrelevant. But part of the challenge is you don't often sometimes you have domain knowledge, like Sarah mentioned, that you can have an expert and say, okay, we have prior research or prior studies that said this is the the subclass of things that are important. But when you're doing more R&D, you may want to take the approach that you don't know what might be important and what might not, and you don't want to throw out variables that that end up being incredibly important. I did a study about a year ago. In my last company we were at, we had our own proprietary version of a feature selection method, and it was kind of based on some genetic programming. But we looked at methods that researchers in genomics were typically using for feature selection, and they would typically use just standard t-test, where if you've had basic statistics, you're familiar with a standard t-test, and they'd have hundreds of thousands of variables, and if the p-value, the t-test between the two populations didn't meet whatever their threshold was, they discard that feature. And we applied our method, and we found that of the proteins that the traditional method found and our method found, there was maybe like 0.02% overlap of where we agreed on what is actually locations on the genome. And so it looked like our method was really bad, because we found very few of what kind of traditional method was finding. But when we actually made a model out of those features, and actually inspected the features and looked at their distributions, it turns out that our features were a lot more predictive and actually biologically relevant. And so I think, to me, this raised an important point, is that feature selection is incredibly important, because that's when you determine what you put in your model. And you want to make sure that you're looking at the process the process of feature selection from a couple of different angles, and you don't discard something unless you have good reason for it. So I don't know. Those are some thoughts that I have kind of about in the medical space. Eric.
Awesome, thanks, Bo. This is a little bit of an expansion on this discussion, but when we talk about thousands of variables and features and things like that, I think one thing that we often don't consider, because we're talking about like an already collected data set, is how much it costs to collect these different features. Like, how much does it cost to take certain measurements? How much does it cost to get a really precise measurement about something? And I know this matters in certain fields, where if you can get really good predictive power, or at least decent predictive power, without having to measure something that's very complicated to get or hard to get, then that's probably a model that you would want to pursue. So in addition to, and there's a lot of like theories behind like information gain and cost, but the economic standpoint on data, especially at scale, I think matters, because if you build a model and you want to sustain it into the future, like let's say we build a production model at LinkedIn, and then we figure out it's really hard to collect one of those features about people, that decision about including it in the model originally has downstream applications. So it's another thing that you can consider, is like the cost, whatever cost is defined as for some of these different features.
Great. So I think we can start moving on into feature engineering. I think I may start there. So when I was starting in data science some years ago, I had no idea what feature engineering was. And I always saw that on maybe some papers and some public out there. And I only thought it was like transforming like integer, or maybe summing two variables. But this is actually quite a complex field, that you have a lot of different kind of opportunities to improve your data set. Right now, I think we can divide feature engineering into two big areas, and one is for machine learning. Like, I don't know, you have a lot of different kind of methods to transform your data from one place to another, or try to some variables, transform them, index them, or whatever. And most of the machine learning models will need feature engineering because of how they work. A lot of times when I was starting with Spark and Python in scikit-learn, I had issues. And the thing is, those frameworks give you the worst errors. I mean, you have no idea of what that error means in the beginning. So after some research, I was like, oh yeah, I need to have all of these variables in the categorical way, or maybe I need to transform this categorical into a numeric one. Okay, so the one big area I can find there for manually changing your variables and transforming them into something that can fit a model. Right now with deep learning, I think the process has changed a little bit, because we're trying to eliminate that part of a data science project and make the net by itself understand the features that are the most important for the process, and also transform them by itself. There are a lot of different methods out there for deep learning that can, I don't know, like in I think a big part of feature engineering is also adding new variables. And when I say adding new variables, I'm talking about how can you improve with the data over over other data sets in your company or the internet, or maybe how can you improve and make the data you have in hand. Because feature engineering also means it's not the same as in enriching a data set with new variables from the out, but you can find a really big set of different opportunities when you try to see, hey, you know, I have these variables now, but what if I join these two variables together with this kind of table I have in this other database, and you can just try it again, and keep trying for making the best model out there. So I think for me, feature engineering in machine learning, not that much in deep learning, is one of the most important into any pipeline. Because if you're not if you're not using your data set at its maximum potential, and you're not transforming those variables into the ones that are going to really fit a machine learning model, I think you're losing a lot of value for this kind of different processes. I think you're not hearing me well. I'm trying to speak here. I don't know if you can hear me, guys. On the chat there, you can say something about if you can hear me.
It's pretty good, Fabio. It's just a little bit in and out. So I mean, it picked up a little bit at the end.
Sorry.
No worries.
All right. Yeah. So I think that's my start on feature engineering. I think you're next, Eric, because you talked.
Oh boy, I got myself into talking. This is bad. What do I have to come up with on the spot? I'm going to actually kick it back for a second, just because, well, there's 4 of us and I think we'll have time. I think I wanted to say one more thing about feature selection, and anyone else who wants to is feel free to jump in. But with feature selection, there's this idea that like you have a complete picture of the features that you need, right? Like, so I think it's an important question to ask is, when do you stop? Like, when do you decide that you have the right features? When do you think that, like, from a business perspective, you can imagine when we ask, okay, we want to build this model, they have tons and tons and tons of ideas. Not all of them are easy to get. And so at what point do you decide that you have a sufficient set before you dive into the modeling process? Because I think that's a hard question, because even in a situation where you have 10,000 features, you still may not have the right ones. And that's just something that I wanted to throw out there as sort of a consideration, because it does connect to feature engineering as well, is deciding when you have the right ones or not.
I think that's a really good point, Eric. You know, another situation that I've seen repeatedly is where you don't have the same features for all of the same population. You know, where you may have a part of your data has, you know, a full set of features, and then part of your data they only were able to collect some of the features. And what do you do at that point? You know, you have considerations of, do you just use the subset of features that go across everything, but you lose predictive power? And it's a problem, and there's not, again, there's not a one-size-fits-all option, but the best thing to do is, you know, I've found that feature selection and model development often are an iterative process. And that's the great thing, and there's a lot of tools in Python and in R that allow for kind of an iterative process. And you know, you may kind of pick a subset of features, start going down a model development process, you know, throw some features out, maybe add some others in, and it'll be a back and forth process until you find you find a subset of features that that you know that works really well. And so I think typically it's not something where you may know ahead of time, you know, this is what we're going to use, and we're just, you know, it's not like a Kaggle example where you have all your features there. This is what we're going to use, and we're going to get a really great outcome. You know, sometimes you need to go back and check and say, do we have additional data that we can bring in? And that's kind of how it works. I think Sarah had a comment on that.
Yeah, so I kind of want to just kind of go over everything we spoke about. So you kind of mentioned, Bo, that, you know, you went through and built a model based not off of domain knowledge, but off of just kind of what the data was telling you. And hopefully I would assume that there would be at least some overlap, right? So maybe you could go into that at some point. But I know I had tried doing something as well like that, and we were trying to build a model, and there was sufficient. Hopefully, if the model is working correctly, or that you're running a feature selection, that there should be some overlap, hopefully, with what people in the domain are kind of saying, are you know, features that should be predicting well. Also, I wanted to say, since I don't know if we'd really mentioned that, the advantages of feature selection, right? So you could throw all the features into your model and, you know, end up with, you know, something decent, but is that going to help in terms of, you know, reducing the training time of your model? Is it easily interpretable if you have all of these features that are just shoved into the model? Hopefully, by reducing and actually running some sort of feature selection, you can improve the accuracy, which is what we're aiming to do, right? Is get the best model and then reduce overfitting. So like Bo had mentioned, things like recursive feature elimination. So going through and eliminating features and checking and evaluating the model, and then removing more features, and then doing that until you have optimized your model. I'm trying to think if I had anything else to say. I think that's good. I think Fabio, you wanted to talk. Oh yeah, okay, we can hear you now.
Okay, yeah. So those are really great points, and I think it's a really good moment to start thinking about how we did things before. And I've been in a consulting firm for some time doing data science for clients that have like historical data, and that they have a way of work with data. And when I asked them, hey, you know, and they also build models. I mean, they build them maybe on some big platform like SAS, or things are easier to work with, not like programming, or maybe just Excel. But when I asked them, hey, how did you guys, or how do you guys choose your variables for creating those models? And they use expertise. That's what they told me. And it's like, yeah, you know, we really know how's the process of doing X. This is what I sell, what I do, and I have a really good idea of which variables are most important ones. Maybe just in someone, I don't know, providing someone with, you need to be able to challenge yourself. When I was talking with some of the clients saying, hey, but you know that now kind of throw those variables into algorithms, and those algorithms will tell you which variables are the most important ones, and some of the variables that you consider for like 30 years of expertise may not be that actually that important for you right now. And they were like, oh, I cannot believe that, and why is that true? And then this kind of barrier that maybe for us that are really into this world of data science and building models every day, it's just really common to throw everything into a machine, and they will tell us, hey, this is the variables you need to consider, and you don't need to be an expert to do this. I mean, as I always say, I'm a physicist that works in a bank, and I don't have this intuition of which variables are the best for predicting anything for a customer in a banking experience. And this is the funny part, and also the interesting part of data science and feature engineering and selection, that you don't need to be an expert in the field to be able to run and create these kind of models. So I think that something we can discuss now is and just before just maybe going into questions, you guys ever had a meeting with the business or some client, and that with these kind of problems I just mentioned, and how you guys manage to I don't know, to inform the other person that now we have algorithms and tools that can expert in deciding which variables are the best for your rules. Anyone?
All right, I'll take it. That was too quiet, too much silence. So I'm going to say I'll give a recent experience where I built a model for a part of our business for sales. At the end, I was really happy. I was giving them a presentation. I'm like, these are the top 50 variables. And the first question after we got done was, what about these? And they weren't in the top 50. It's like, all right, I just spent so much time doing this. But it's often, at the end of the day, I think you have to be able to make a case, not only to say what's important in a model, but also help them understand why things that they thought were important maybe are not. It doesn't mean necessarily that the model says their feature is unimportant. Maybe their feature is highly correlated with one of the resulting features that came in the model. But I think being ready for that conversation, it's easy to fall in love with any model you build and you're like, I picked the best features, but you're going to get pushback, especially if it doesn't fit with what the business believes or it goes against the grain of what they expect. So that's how I'll kick off that conversation.
I think that's a really good point, Eric. And one, you've brought up this point a couple times, but when you're choosing features, there's a number of considerations. Not only do you want the features that contain the most information content in them that's going to let you have a good prediction, but you want features that are easy to collect or readily available. But again, back to the discussion is, how is your model or your research going to be used ultimately? And that's a huge consideration. If it's something that won't resonate with who you're delivering the model to, or if there's going to be some problem with a feature that you've chosen, then that needs to factor in as well. I think that that's definitely an important consideration. I thought that we could each spend a little bit of time talking about some of the methods that we use specifically for feature selection, kind of what some of our favorite methods are. And I'll start off with that, and with the understanding that methods always vary. But I like to think about features as in a way that they're carrying information, and they're carrying information content. And I think I'm not an expert mathematician, but Shannon has some really interesting like entropy measures and other things like that. And if you think about features that you're including on your model, you want ones that have the most information with them. And so I like that as a general framework on what should I be choosing to keep around, and what should I not be choosing to keep around. Some methods that I use frequently, I've actually used random forest as a feature selection method. A lot of people don't think of it that way, but it, you have a ranked variable importance. It's really a lot of times it's a great first pass if I have a ton of features and I just want to see what would surface to the top of a quick random forest, and that wouldn't be my end kind of my end of decision, but it's very useful in data exploration. In R, there's a package called Caret that's kind of like the scikit-learn of R, and they have a whole vignette of like 20 different feature selection methods, including genetic programming methods, and there's some really great options to try out there. So those are kind of two of the methods that I use for larger data sets.
Okay, I can talk about my experience. So most recently, I've been involved in a lot of NLP projects. So especially in NLP, you end up with a lot of features, and kind of kind of to like Bo's point, and what we've all kind of experienced is you end up with this massive feature space. And in our case, when you're dealing, well, in the projects that I've worked on, you kind of don't want to get rid of any features, right? So what we end up doing with text data is probably using some dimensionality reduction method. And so something like principal component analysis or single value decomposition end up being really good methods of kind of encapsulating all of the features into a reduced space, and then basically evaluating that based off of the explained variance. So you want to maximize how much variance your model's explaining. And so, I don't know, in some cases, you might just choose a number and say, hey, I want this many features, and then that ends up being your feature space. So, and then just trying to maximize that with how much variance, like trying to, the trade-off between, a few features and how much variance you're explaining, so.
All right, I think I'll go next, and I'm going to talk about Spark. That was kind of anticipated. So I think I really like. I mean, Spark is not that like complete or full with different kind of estimators and machine learning models as like scikit-learn or maybe R with Caret, but I are using big data. That may be the case for most of us right now. And you take a look of PySpark, and that's the Python API for and inside of that like web page, you have all of the different kind of structures, transformers, and selectors that Spark has available. And I for selecting, we only have like 3 or 4, but they're quite interesting. One of the things I use the most, apart from also random forest as well, as a first like my baseline for selecting variables, is the chi-square selector. The chi-square selector is really interesting. I mean, I don't have the whole time to talk about it, but take a look on that on Spark. And you have 2 other kind of funny ones. The one is the R formula. The R formula is a way you can create and select variables depending on a formula you create for the different variables you have available. And the last one I use a lot is vector slicer. The vector slicer is really useful when you have this kind of, maybe you have a vector of features, but the first 20 features are your zeros, and that's really annoying to work with. And what if you have a terabyte of data with that kind of problem? And that's not easy to solve. But with Spark, you select, hey, I don't want any zeros in my I don't know, in my transformer or in my feature selection process or wherever, and then you can just erase them. And also a lot of things for creating models in machine learning, like one hot encoders, string indexers, index to string. And also, I think we didn't mention this, but this is really important for feature transform engineering in most cases, is standardizing and normalizing your data. A lot of times, and you need to do this for some machine learning models, and with Spark it's really easy. You have something called a standard scalar. Just take a look, and yep, that's it for me.
All right, I'm going to unmute myself. I'm going to say something that can be unpopular with people, is that, like, there are a lot of different ways to do feature selection. And at the end of the day, in a few years from now, so much of it is just going to be automated that we may not even be having this discussion. So, and while I think it's important to understand what features are chosen, like we're seeing with deep learning, we're seeing with a lot of the libraries and things that we set up now, we're trying to make it as easy as possible to do feature selection. And so while a few years ago people would say, well, there's no way these things can understand context, I think that's changing a lot. And so I think it's great to know all the different methods and understand what they do well, what they don't do well, why they might get you a weird result. But it's also important to understand that as a data scientist, like, your time in a few years may not be spent very valuably if you are spending tons of time on feature selection, whereas right now that's a little different. Just something that is on my mind, and that's because I spend a lot of time doing feature selection, and I wonder if it's going to be the same way down the road.
That's a really good point, Eric, and that would maybe be a different office hours topic of where we think data science might be in a couple of years from now. Bavio, did you have something to say? Oh, nope. All right. So one, I think we're almost to the point where we can answer questions. One point that I wanted to bring up, just in relation to feature engineering and feature selection, is particularly in medical data, I've found that feature engineering can be particularly important because, as Sarah mentioned, it can reduce the dimensionality of your data set by creating a new feature, a new variable that captures a lot of the information or variance and that is explained by multiple other variables. One example that I think is often overlooked is sometimes the absence of data is data itself. That's especially true with medical data, where if you have count data or something like that, sometimes whether or not someone has a positive result or the absence of information is just as important. And so I've seen a lot of predictive power where where I've added they did not have a doctor visit as a variable, for example, and that turned out to be really important. Whereas otherwise, the algorithm might struggle to try to create that same information out of multiple other variables. So that's something to think about, is sometimes the absence of information, you can code that as a variable, and that itself can be very predictive. So, all right. So I don't know if anyone else has any kind of thoughts before we go try to answer some questions.
No, I think we have like 20 minutes to answer questions. So I think I'm going to start. So I'm just gonna randomly, not so randomly, choose one, and and one of the things I see here is this one. What are the methods you guys have used to create new variables from existing variables? Two-way, three-way interactions. How to decide which variables to interact and how to interact. I don't fully understand the question. I don't. I mean, I understood the first part. The first part. So I'm gonna answer the first part of the question. And for the first part, I mean, when you for creating new variables from existing variables, that's all about feature engineering, and and we have a lot of different kind of ways of doing this in different packages. For me, the ones I use the most actually for Spark are transforming categorical variables into numerical variables. I mean, I think this for me is the common like the because almost every algorithm of machine learning in Spark only works with numerical data, and also the funny part here that you need to go back, and because you cannot say to the business, hey, you know, the most important thing here is that you have to optimize 2 to get 4, and you really need to give them the information that they need, and you need to understand them all afterwards. So I think a really good both in scikit-learn and Spark is where you have a transformation from categorical to numerical. You have the same exact kind of function to go back. So I think that's my most common task.
Thanks, Fabio. I wanted to attempt to answer the second half of that question about what do you do about variable interactions? And a couple of thoughts about that. One, variable interactions are incredibly important when you're trying to use linear techniques like linear logistic regression to approximate nonlinear relationships. And so often you're usually stuck with domain knowledge of saying, I know that these two variables in, like, for example, in a biological system, they probably interact with each other somehow. So you might create another variable that somehow captures that relationship between those two variables and then plug that into your model. More complex machine learning methods can approximate those variable interactions kind of just built into the method. But, you know, ultimately, you know, and this is a completely different topic for another day, but the scientist in me is always a little bit uncomfortable with the approximation of machine learning algorithms. I know that we throw more and more data at a machine learning algorithm, we get better and better accuracy. But you know, one method that that captures interactions between variables without having to know them beforehand is genetic programming and linear genetic modeling, and we can talk about that some other time. But usually, if you know that there's going to be an important interaction between two variables, you might have to create a variable yourself beforehand and plug that into the model and see if it sticks. And if it doesn't, then that's your answer.
Okay, I think we can go to a different one now, and I think this one is for Sarah. And Kruti said, in case of NLP, how do you limit your dictionary size of words / n-grams?
Okay, so I think that's a good question. So in terms of building out your dictionary when you're looking at a lot of text data, I think the first pass is like, okay, well, first thing I would look at, what type of text do I have, right? Is it long text or is it short text? Because that'll hugely kind of determine how I'm going to like proceed. Then there's very simple things that you can do because you're going to essentially take each sentence and tokenize it, and from there, like removing punctuation, removing stop words, removing anything that is just extraneous to what you know is kind of the meat of your of what you're trying to look at. And things like TF-IDF would do that for you. So using like the parameters like minimum and maximum probability, frequency that it's in a document. In a corpus. So so there's really easy ways to get rid of kind of fluff words. But then also you mentioned n-grams. So n-grams is actually a really good way to look at, so especially bigrams come up very frequently. So you'll see words like red and wine, which by themselves might not be that useful, but when you incorporate bigrams into your model, you can look for words like red wine, and that might actually be a good feature. So I hope that helps.
Yeah, I think that's a really great answer. I would love to have that answer like a year ago when I was starting with this NLP things. So I think one interesting question here from Matteo Rinaldi is, do you have a sense of which methods are more stable in terms of efficiency as the sparsity of the data set increases? Someone wants to say something? I mean, for me, in my own experience, I mean, I like a full answer to this question, but and actually, I don't know if you mean for selecting or for transforming variables here. I'm gonna just I don't know, think is for transforming variables, and I think for the efficiency here, I think that may depend on the framework you're using for doing these transformations. I'm a big defender of Spark for sparse data because you have a native way of expressing sparsity into sparse vectors inside of Spark, and when you have that, it's just really easy and fast to run any algorithm for transforming variables. It's just really fast in Spark when you have sparse data. And also for selecting variables, I think the one called the vector slicer, when you have a lot of zeros and you want to get rid of them, it's actually really easy for doing that. And we have a lot of sparse data, and it's really easy. Even though if you have a terabyte of data, if you have a really good cluster and it's well balanced, for me, one of the best tools for sparse data sets is Spark right now. All right, someone else want to add something, or we go to the next question? Okay, so next question, or Eric wants to say something? No.
I was going to say next question, so.
All right. All right. So I'm gonna use, because we had a question in the beginning, and so Aparna, she had a question, and she asked, how useful is the built-in method RFE of scikit-learn? I think RFE means here recursive feature elimination. And I don't know if you guys have used that before. So I have, I don't know.
I mean, I can, so I've used it. I will be very honest, I have no idea what it's doing internally. So let's just lay that out there. But it produces relatively comparable results to a lot of the best known packages in R. So, I mean, that was my main reason for using it, was to compare results. So certainly in Python and R, I don't see a huge difference between some of their best algorithms. Yeah, and I actually didn't know what it stood for until just now. So I just like to lay it out there and be honest. So I think even if that's not what it stands for, Fabio, I think I'm just going to refer to it in that way now.
Yeah, I'm kind of sure that it means recursive feature combination. I think it works by subsetting. I think it works by subsetting the data you have, the amount of variables you have, and it will go try to see which subset of the data is the best for explaining your data set. I think that's the way it works.
I think you're exactly right.
I haven't used it before. I just remember seeing it somewhere. I don't remember where, but yeah, I'm not an expert in scikit-learn here.
Yeah, so I think what it's essentially doing is going through and, like you said, Fabio, just removing features and then reevaluating the model and then finding a perfect subset, depending on, because you'll specify how many features you care about, and it'll continue to build a subset until it finds.
I think I'll use it more now.
It sounds, I mean, conceptually is similar to like a stepwise regression.
Yeah, it's like stepwise regression.
Yeah.
I have another question here. Blah, 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 blah. How accurate was the domain knowledge? Oh, this is a good question here. I don't know if it's well phrased, but I'm gonna just grant. How accurate was the domain knowledge? I wonder sometimes that the domain expert introduces a level of bias into the model. So do you guys think that if you're an expert of, I mean, let's take this guy who has been working with this data set 30 years, and now he's an expert in machine learning. Do you guys think he will add a level of bias when selecting and transforming variables?
I think that's unavoidable. I think we always add some sort of bias, and I think the way that I approach domain expertise is I try to approach it with a healthy degree of skepticism. I think there's a lot that can be learned from domain experts, and so you listen, of course, listen, because they have knowledge that you're not going to have, and listen to them carefully, but also keep your eyes wide open that they may have been doing something for 30 years that turns out to not be correct or turns out to be suboptimal. And so I think you need to be willing to trust the domain experts, but also be willing to prove them wrong if they are wrong, and make sure you have evidence for that. And something else that I want to add is if you can find a way to turn bias into a variable, then that's even better. If you have, for example, if I keep going back to medical examples, but if you have a couple different doctors in your study who are all measuring the same things as patients, make the doctors a variable, and that can hopefully correct for any bias that may be introduced by those differences. So that's kind of like common sense stuff, but those are my thoughts.
I'm going to jump in and say, at the end of the day, between domain experts or if it's somebody who just walked in the door, the main question that people care about is, does the model do what it's supposed to do? Like, if it's working, then I'm fine with the domain expert being like, I'm the reason that it's working, as long as the model is doing what it's supposed to do. And you're right, because bias is going to be present no matter what you do. And at the end of the day, when it's outside of data science and you're presenting a model as a data product to other people, they just want to know that it works. And so that, of course, involves probably dealing with issues of bias before it gets there. But I think at the end of the day, you don't want to surface like, oh, this came from a domain expert or this didn't. At the end of the day, people just want to know that something does what they expect it to do.
Yeah, I was going to agree with that. Is that you know, you're not going to know until you evaluate the model, and you can test multiple models and just check them against each other. And you could talk to one person and they can say, "Oh, well, I swear by this and I swear by that," and you know, they could all be wrong or be right. So,
Yeah.
but most important thing is just to evaluate the model and make sure it's doing what you expect it to do.
Yeah, so I think we can go to a final question here, and I think it's really close with what Eric said before. Is is it worth to learning how to automate things such as feature engineering? And I think what Eric said is really true, and I also put forward this thought right now. I think we will write less code from this year to, I mean, every year we will be writing less and less code. And I think AutoML is not gonna replace data scientists, but it's gonna help us just don't do these steps that are may take a lot of time for when we could be creating different business meetings. And I think is if you want to be a researcher in the area, it's really important to understand how to automate processes. If you're a final user, I think it's not to understand how you automate feature engineering. I think it's good to know that there are people out there like Google who with AutoML, or Deep Cognition with their software for feature engineering, like with AutoML2 and H2O. So I think it's important to understand that that can be done, and more for me that understanding how is it done. and I mean, if you're a researcher in the area, of course, just go ahead. And if you have some time to read some papers and read some information about it, that's great. I don't know if you have some more thoughts about that.
All right, I have one final thing to say. You're right. Because there's such huge business value that's unlocked by automating these type of things, it almost guarantees that a lot of the really big research groups are doing it. And so we see a lot of downstream results from these research groups because they build a tool internally or they do it for whatever, because it provides so much business value that I think it's wrong to think that it would be a wasted effort for every company to replicate the same type of thing when a lot of this ends up being open sourced in the end. Because if you think about the people who are developing Python and developing R and RStudio, they have a vested interest in growing their user base. And they also have a vested interest in making usable packages that are going to do a lot of this automated stuff. So especially if you're in a smaller group, I think maybe it's not the place to be spending your time on developing all of this automation when a lot of it is going to be rolling out and has rolled out as, you know, publicly available data products.
Okay. Well,
I was just going to say I agree, and I had great points by both of you, so I didn't have anything more profound to add than that.
Yeah, same here.
all right.
All right.
All right. So I think it's just right on time. I think we can just start saying goodbye, and thank you all of you guys and all of you guys hearing this we have, and for being here and supporting us. And I think tomorrow we'll have this articles created by people that are be waiting for the articles of you guys on how we. And remember that all of these videos are saved here in YouTube, and you can just watch them and re-watch them again. and if you feel like you want to see our faces again. So we're
Yeah. All right. All right. Thanks, everybody.
all right.
Have a good night.
Good night,
Thanks.
Have a great
everyone.
week.
Bye
See
bye.
ya.
You too.
Bye.
Bye.
Bye.